So we are starting. I remind you that yesterday we started this two-state model about a gas of particles, non-interacting particles. Those particles had two energy levels, so two-state model. We use micro-canonical ensemble. Okay. So we have a box. It doesn't really matter if we have a box or not. We look on each and different particle. The energetic spectrum of each particle is 0 or epsilon. We have in total n particles inside the system, n particles in the system. They are not interacting. We used our algorithm and eventually obtained the following result. What was our result? The energy of the particles, which is the average energy of course, was n epsilon e to the power minus epsilon divided by k Boltzmann t divided by e to the power minus epsilon divided by k Boltzmann t plus 1. Right, something like that. Let me check. I think this is correct. Seems reasonable. Yep. Great. Now, the idea was to compute the heat capacity. Why the heat capacity? The heat capacity is a measurable quantity. You can go to any lab, and usually what you do, you heat up the system a little bit. Again, you see how the energy is changing due to your application of heating process. So the heat capacity, C, it is dE to dt. In our case, the volume is constant or the pressure is constant. Well, the particles are not interacting and there is no volume inside the system, so we didn't really care. The number of particles is constant in our case. So we want to obtain how C behaves as a function of the temperature of the system. So this is the idea that we want to observe for a two-level system. What we want to do, E is provided, we have to take a derivative, right? So C equals d to dt of what? Of n epsilon, and let's rewrite it for simplicity as 1 over e to the power epsilon divided by k Boltzmann t plus 1. Right. So this is the expression. Okay, so I would like to do it as d over d epsilon divided by k Boltzmann t of n epsilon divided by e epsilon over k Boltzmann t plus 1 multiplied by d epsilon by k Boltzmann t by dt. Okay? Fine, so it's just, instead of taking a derivative with respect to t, I'm taking the derivative with respect to this whole thing, and then taking the derivative of this whole thing with respect to t. Okay. Why I'm doing that? Because my function, the dependence on t inside the function is over epsilon divided by k Boltzmann t, so it's easier to do it that way. Great. So what this guy tells us, so n epsilon stays exactly n epsilon, nothing happens. I'm taking the derivative of 1 over e k Boltzmann t plus 1, so what I obtain is 1 or minus 1 divided by e epsilon k Boltzmann t plus 1 to the power of 2. Okay, so this is this whole thing. This is what it gives us. Okay. Now we have to take the next derivative of this guy, which is epsilon divided by k Boltzmann stays the same. So we have epsilon divided by k Boltzmann. And the derivative of 1 over t with respect to dt is minus 1 over t squared. Okay? So minus 1 and minus 1 cancels. And what we obtain, it is 1 over t. 1 over t. What else do we have? Let's take it. Epsilon divided by k Boltzmann t. Epsilon divided by t. So we have n epsilon to the second power divided by k Boltzmann. Have I forgotten something?
Yeah.
The exponent, right? So we have an exponent of epsilon divided by k Boltzmann t. Okay, so what we have, n epsilon squared k Boltzmann t squared, and here we have an e to the power epsilon divided by k Boltzmann t divided by e to the epsilon of k Boltzmann t plus 1 squared. Okay, so this is our expression. So what do we know? Let's look on the two limits. First, the limit when t goes to 0. So this is t goes to 0. When we look on the t goes to 0, what happens to 1 over t squared? It diverges, right? So we have some sort of a divergence that comes from 1 over t squared. Okay. Now, we also have the dependence on t inside the exponent over here. So we have an epsilon divided by k Boltzmann t. When t goes to 0, what happens to this guy?
The exponent explodes.
The exponent explodes, right? So the exponent explodes. So the exponent explodes and it diverges also, right? So we have a divergent term that comes from t squared. We have a divergent term that comes from e to the power epsilon divided by k Boltzmann t. But we have another term, which is the exponent of epsilon divided by k Boltzmann t. So this term is also diverging.
Yeah, but it's diverging from below.
So it's converging to 0.
It's converging to 0.
Right. So we have divergent parts. Those guys are diverging. And this guy, is converging to 0. And the question is, what happens faster or stronger? The divergence of this to infinity, or the convergence to 0 because of this guy?
Of course the convergence from 0 because it's squared.
It is squared, right? So the idea is, when t is very, very, very small, plus 1 is completely negligible, okay? So in this limit of t goes to 0, the only thing that matters, forget about all the constants, etc., etc. The only things that matters, so c, when t goes to 0, goes like 1 over t squared e to the power epsilon divided by k Boltzmann t divided by e to the power of epsilon divided by k Boltzmann t, and we have put a power 2 over here. Why? Because we have second power over here. So this is e1 over t squared e to the power minus epsilon divided by k Boltzmann t. So I again ask the question, this guy diverges and this guy converges to 0. What is stronger?
The exponent.
The exponent is stronger because it has 1 over t inside. Okay. So what we obtain in the limit, so this guy goes to 0 when t goes to 0. So what we have in the limit of the low temperatures, the convergence to 0, okay, all of this derivative or all of this expression has to be positive. It cannot go to negative values, so it has to grow. Right. Great. So we have a growing function as a function of temperature of the heat capacity. Now, this is reasonable. Why it's reasonable? I have a system. I put it in the 0 temperature. In the 0 temperature, probably all the particles don't have any energy and they prefer to stay in the lowest, on the ground state. I heat the system a little bit, provided another energy, And what happens to the energy? The energy grows. Hence, the heat capacity, which is the derivative of the energy with respect to the temperature, is positive, so it's growing. Great, so this is one regime. The other regime is what happens when t goes to infinity. When t diverging. Usually in physics, we look on the asymptotic behaviors. In the middle is always a mess. It's not a problem to actually plot this, right? But when you need to understand something, I mean understanding from the math, you usually need to do some asymptotic assumptions or asymptotic calculations. And there are general behavior near zero, and there are going to be general behavior in the other limit when t goes to infinity. Okay, so what happens when t goes to infinity? Okay, 1 over t squared converges, goes where? So again, we don't care about this guy, right? So we have 1 over t squared, which is contributing something. What else do we have? Where goes the exponent?
1.
Goes to 1. It's not going to 0. So e to the power, some t goes to infinity, so e to the power of 0. E to the power of 0 is 1. So we have 1 over here, and what we have over here is also 1 plus 1, so it's doesn't matter, so it's 2 squared. It doesn't really matter if it's 2, 3, 4, 5. Okay? So what we have, 1 over t squared, also goes to 0 as t goes to infinity. Okay? So what we obtain is that we have a decreasing function for high temperatures. Low temperatures, heat capacity goes up. High temperatures, heat capacity goes down.
So there must be some
And probably there is some
maximum.
So, well, maybe there are 3 maximum or 4 maxima, but there are actually only 1 maximum. Okay. This maxima has a name called the Schottky anomaly. Schottky anomaly. Oh, I'll describe why anomaly. But Schottky, the people who studied electronics over here, Schottky diode, stuff like that. So Schottky was originally German, afterwards an American physicist working on semiconductors. So why it's called anomaly? It's actually, think about it. I heat the system up, the heat capacity goes down. So the energy grows. I heat the system more, the energy grows. I heat the system more, the energy should grow because I'm heating this damn thing on and on and on and on. Why the heat capacity goes down? Okay, think about it. I'm heating the system, more particles are occupying the excited state. I heat the system a bit more particles occupy the exciting state. Why it goes down?
Because maybe it's become maybe because it become too homogeneous.
No. So, but a little bit of that. It's saturating, right? Think about it. The number of particles that I have inside my system is constant. I'm not letting particles inside the box. I'm not letting particles outside of the box. The number of particles that it's inside the system is constant. So as I continue to heat the system up, the number of particles that occupying the excited state grows. It grows and grows and grows and grows, but at some point there's almost no particles that can occupy the excited state. So the energy is converging to a constant value, which is n maximum multiplied by epsilon. The moment that it happens, the derivative, which is the derivative of the energy with respect to temperature, has to grow down. Okay? So this is why it's called anomaly. The expectation, the regular expectation of the heat capacity is to go up. Maybe it converges to a constant, but not to go down. But in any case, when you have 2 states, or something that looks like 2 states, right, you will always get this behavior over here. You can break it because, for example, let's assume, and now why semiconductors? The people who know, there are conducting bands and there are separation, and it looks like 2-state system. The conduction of in semiconductors. You learn about it in another class. But in our case, if if you look on each and single particle and its energy, epsilon, so there is 0. This is energy. This is epsilon. And the particle, as you heat the system up, can go from here to here. Okay? There are no other allowed energies, so it's going to be stuck over there. It's definitely not going to get down, right? Because there is a lot of temperature, a lot of energy that we put inside the system. And this energy, well, it's not absorbed anymore. But if there is some way up, another level, right? So there is another level up. It's called epsilon 1, it's called epsilon 2. What will happen? So you look on this anomaly and say, well, yes, it's going down. Let's continue this plot a little bit. And it goes down, goes down, it goes down. Okay. Suddenly, you start to see a second hump. Why it's going to increase again? Because at some point, you pump so much energy inside the system that this particle actually now can make a transition and hit the next level. You have to supply enough energy for this to happen, right? You have to supply enough energy for this to happen, but eventually if you're heating up is supplying energy to the system. So eventually they will start to go up. If there is no other level above epsilon 2, eventually it will go down again, right? You don't care. So basically those humps, those anomalies, they happen in any situation where you have a sufficient separation between energetic levels inside your system. If the levels are very close to each other, nothing like that will happen. Right? But the moment that you have a big gap, like in semiconductors, you will start to see those anomalies. Great. So this was the concluding example of microcanonical ensemble. You will solve another examples during the TA session, tutorial session, but for us, we mostly use microcanonical ensemble in order to get to a much more efficient and much more realistic ensembles like the canonical and the grand canonical ensemble. So if anyone has questions about this example or the microcanonical ensemble, this is the time to ask. Yes? Yes.
You started with a term for E which had negative terms inside the...
Bring this guy down. And epsilon, e to the power epsilon divided by k Boltzmann t multiplied by e to the minus epsilon k Boltzmann t plus 1. Right? And then this will become 1 and this will become positive. Right.
I missed it.
You're right. Yes?
I didn't understand why if we have another energy level,
So if you have another energy level, let's assume that in our original setup, there was no epsilon 2, and you're absolutely right. But let's assume that the real system, there is 0, epsilon 1, and far, far, far above, there is epsilon 2. Okay? You will discover that there is indeed an epsilon 2 if you heat up the system. But let's assume that you have a system of particles or something. Okay, and you start to heat it up. Right? You're heating it up, it goes up. The heat capacity, you measure the heat capacity, it's possible. And then it starts to go down and say, oh, I have a two-level system. I have a gap. And somehow you can, from the behavior where the maximum is located, you can find this gap, delta. Okay? The moment that it goes down, you understand that, well, probably there are no additional energy levels above it. Okay? But because you can do it, you say, well, why I won't heat the system more and more and more and more? Well, nothing happens, it just converges to 0, but suddenly it starts to go up again. You said, oh, I discovered an additional level. It's called delta 1, and this is going to be delta 2. Okay? And this, by heating the system and looking on the appearance of those humps or those anomalies, you can understand what is the structure of your energetic spectrum.
I understood that. I'm just saying I don't understand why does it go down in the first place rather than saturating? That's what I didn't understand.
Because it's derivative. Energy converges to a constant, right? energy converges to a constant. Okay, so you take a derivative of a constant, it has to go down.
Stas,
Yes.
both of the maximas are the same height?
No. So you have to you have not exactly, and you have to compute. You have to take this model and compute the energy and do everything that we have done so far in order to compute what exactly the height of this guy and the height of that guy, etc., etc. So I cannot really say what exactly is going to happen.
Not even predict if the first one is higher than the second one?
No. So the truth is that I haven't done it. Maybe it's easy to do this, but I will tell you later today, hopefully today, that even if you hit me with a stick, I won't do it with microcanonical ensemble because it's hard. Okay, I'll explain a little bit later. Because if you remember how we done it, we have taken two states and we performed this operation of choosing specific. So there was combinatorial problem that we solved, right? Now, if you add three states, the difficulty of the combinatorial problem jumps. Okay? It's not as easy as to choose, like, oh, I'm choosing only those particles that are sitting at epsilon 1. Now you have to choose some of the particles sitting over here, some of the particles can sit over there, and the combinatorics become harder and harder, and I don't want to do it. In canonical system, I can, and maybe it's, it's easy over there. But with microcanonics, no. Yes?
All the peaks, the heat capacity have the same value?
So this is what he asks, and I don't really know. The answer is I don't really know, and I don't want to compute it with using microcanonical ensemble. I want to compute it using canonical ensemble, and I will describe to you why. Yes?
Assuming we have only two states, does it mean that as t goes larger and larger, it becomes easier to heat up the system? Because the energy is smaller?
So look, it's only a model, right? It's only a model. It's and the heat capacity. It's not. You're not heating the system. You're not heating the system. It's not about heating the system. The energy is not growing. You basically heat the system, and the heat cannot penetrate inside. That's what it says to it. The system does not absorb heat in terms of energy. That's what's happening. Okay. All right. So we are going to our next ensemble, which has a very nice name of a canonical ensemble. Okay. So the line of thought that I tried to convince you is to say, if I have an observable and I want to compute its expectation value or its average, right? I have to go and sum up, right? So this is the definition of what expectation is, the ensemble average of f of I, right? And here I have O of I. And for the energy, so this is a general observable for the energy, E, which is our energy, is summation over all the possible states of the system. Let's assume that we have states, and if we have a classical system. So for the classical system, we can describe what the states are by separating in the separation in phase space. Is going to be Fi Ei. Great. For the microcanonical ensemble, we tried to find almost the simplest description. So I don't know what happens exactly. I'm using statistical assumptions about those guys over here. Okay. Some specific statistical assumptions about those guys. Okay. So microcanonical ensemble. Microcanonical ensemble. The assumptions were E uniform or Fi uniform, Ei uniform. If you think about stochastic or random variables, probably the easiest one to take on care of is the uniform stochastic random variable. Of course, you have very specific cases like Bernoulli, which is the simplest one. But if you don't want to do something which is not two-state, you need to use uniform random variables. Great. Now the next step, if you remember how probability class is being taught, is you say, okay, I have this specific stochastic random variable, and I'm going to use something else. I'm going to use not regular probability, I'm going to use conditional probability. Right? So what is conditional probability? Think about the following system. So if I have a dice, okay, and I roll it, so this is my microcanonical ensemble. I assume, well, there is a chance of 1/6 for each specific state, right? Each specific state have a chance of 1/6, and all this is described by a random variable which is uniform. All the states, which is 1 is 1/6, 2 is 1/6, 3 is 1/6, 4 is 1/6, etc., and 5 is 1/6, and if you're already doing it, and 6 is also 1/6. So those are the different states of my system, and they are completely uniform. Okay? In what sense they are uniform? No, 2 is not 4, because maybe I betted on 4 and not on 2, but as in terms of probabilities, they are exactly the same, and I describe them in the same saying that all the energies are also the same. But what we can do when I'm talking about constraining random variables, let's assume that instead of doing this with one dice, I'm doing it with 2 dices. So I have a green dice, and I have a black dice. Okay. And I roll them. And the constraint saying, the total sum equals 6. Right? So the moment I roll those dices, all right, first of all, not every outcome of the green dice is possible, right? Not every outcome is possible. Why? Well, because if the outcome of the green dice is 1, the outcome of the black dice is going to be 5. If the outcome of the red dice is 2, the outcome of the black dice is going to be 4. And in total, I can count this. I can do this for 3, and I can do this for 4, and I can do this for 5. Right? So the moment that I have constraints inside the system, those constraints affect the values that I can observe for my system. So let's consider that beforehand my system was completely unconstrained. This is the simplest possible description. This is my dice. I roll it out, and the different states are described by simple random variables which are completely uniform. Now, if I'm constraining those guys to another dice, suddenly I see, well, you know what? So here is 3. I have a specific less number of outcomes that I can have, right? So it's 2, and it's going to be 1. Okay, this is simple enough. But what will happen if I'll constrain it to another dice? So we have green, black. Let's have a red. The moment that I constrain my system to 2 dices, one of them is black, one of them is red. First of all, the number of the outcomes that I can obtain is actually becoming smaller, right? But for each outcome of my dice, there are several outcomes for the combined system, which is black dice and red dice, right? So when I'm looking on the outcome that I have 1, the sum is still 6. So when I have 1, right, what can happen to the black and red dices? Right? So if I have 1, we can have, for the red dice, we can have 1, 2, and for the black dice, we can have 4, right? So this is one state. If I have 1 and the red dice has 2, the black dice have to have 3, right? Okay. I still have 1, and if for this guy I have 3, the black guy have to have 2, and the last one, promises this is the last one, if this guy has 4, the black guy has to have 1. So I'm looking on the outcome, the single outcome. This is my state now. So this state, if beforehand it was a single state, it has a specific probability. I conditioned on something and I looked on a system which was combined of 2 dices, and suddenly the probability of 1 became what? Instead of 1 over 6, it became 1 over 5, because those are conditionally reasonable probabilities and homogeneous. Okay, I increase the system to which my blue dice is glued, right? And suddenly the number of states became different. And for each realization of my state, the other systems, they don't really have only one outcome, right? They have many different states, right? So this is the idea that we're using in canonical ensembles. We look on the system, but instead of saying, oh, I have a very specific energy, I'm saying something a little bit different. I constrain it. I constrain it. So the idea is called heat bath or reservoir, whatever. And it's to say the following. Beforehand, you had a system, you can call it a macrocanonical system, macroscopical system, and you define its energy, and the energy was constant. And for all the different states that the system could occupy given this energy, all the different states had exactly the same energy. All right. Now, we're saying, so this is your system. This is your, let's make it green. Let's call it green. So this is your system. This is the system. Like your green dice. You put it in contact with many other different systems. Black dice and red dice and etc. etc. So you have the wonderful many different systems that are in contact with your system. We call this heat bath or reservoir. Okay. And you're saying the following thing. The total system is constrained to have a very specific energy. Like over here, all right? Or over there. I said constrain the total sum equals to 6. So this is the global constraint that you're using, like in microcanonical ensemble. You're saying the energy is something. Okay? Over here I'm doing exactly the same thing. The energy, not of my green dice, is something. The energy of the whole system, which is my system, plus reservoir, so total system plus reservoir. I'm constraining the whole system, okay? I'm constraining the whole system to have a very specific energy. Okay. But the moment that I constrain the whole system to have a very specific energy, I'm allowing some exchange between my system and the heat reservoir. So my system can actually have different states. Different states. It's 1 and 2 and 3 and 4 and 5. Okay? So, for example, if I have 4, there are less states for my green dice than if I have 1. Right? So, if I have less states, maybe the energy is smaller or the energy is larger. The moment that I can have actually different values of my outcome, each value corresponds to different states of the heat reservoir. The moment that there are different states of the heat reservoir, all right, maybe there are different probabilities for each state over here. Okay. So if beforehand I just told, well, each state has the same probability. What is the probability? Because it's homogeneous, it's just 1 over the number of the total number of states. But now it's different. Right? Why is it different? It's different because the system, for each state of the system, there are different number of states for the reservoir. Okay? So what you do is the following. You say, I constrain. What do you constrain? You constrain the total energy. So E total, you're constrained. Okay. You assume that everything is homogeneous, and you ask the following question. What is Fi? Fi is probability of the system to be in state I. So what do you have to do? So this is a single state, right? But for each single state of my green dice, there are many different states of the black and red, right? So, well, it's just constraint probability, condition probability, so it equals to the number of states of the reservoir divided by the number of states of the total system. Now, the total system is constrained, so you have to compute the number of states of everything when your system is E total. You don't have a whole sample state for any given energy, for any energy. You said E total is constrained. So what is the total number of states over all of this guy? I'm using a microcanonical description. The microcanonical description says, well, just count the number of states. Each of them has exactly the same probability. That's what I'm doing over here. I'm saying the probability of each state is 1 over E total. How many states, for a given specific state of my system, how many different states there are? I have to go and compute the number of states for the reservoir. But what is if the total energy is E total? What is the energy of the reservoir? What do you say? So if this corresponds to state I, for state I, there is a specific energy. Let's call it EI. So if this is E total, this is EI, so the energy of the reservoir is E total minus EI. This is just a formula for condition probability. I compute the total number of states, okay? I'm looking on my system, which is subspace of the total sample space, and I'm saying, oh, I need just to count the total number of states that corresponds to a specific of the reservoir that correspond to a specific given state of the system. You can say, well, here is one state, maybe in the heat bath, there are also just one single state, but it's not true. As you've seen in this example. I constrain something, I look on a specific state, right? For example, like I wrote out number 1. There are many different situations that for the rolling of the black and the red dice. And this is just the condition probability formula. That's it. So what we've done in canonical ensemble is we are doing the following thing. Instead of saying all the different states are exactly the same, I'm including this heat bath, making a contact of my system with the heat bath, and saying, well, a system can have different energies. So EI is energy at state I. So I'm looking on a very specific state with very specific energy. Great. But for this very specific state with very specific energy, due to the constraint, the heat reservoir can have many states. How you find the total, the probability? You assume this homogeneous assumption, and you say, well, I count the number of states for the reservoir, and I divide it by the total number of states of the system. That's it. Great. You see, we haven't used anything like in thermodynamics. We look on the macroscopic of picture, we assume something very, very, very simple, right? We use, oh, this is a microeconomic ensemble, this is slightly more complex ensemble, some additional conditions on the probabilities, and from here you start. In microcanonical ensemble, the next step after I decided all the states are equally probable, said, oh, there is a path to thermodynamics. Right? So what is the path to thermodynamics? To use entropy. To use entropy. We are going to use exactly the same idea in the following, because this is not enough. I don't want to count states. If you remember in probability, you start the class with counting different states, and at some point you learn different tricks, and you stop counting states. You do something else. You condition, you do a bunch of tricks. The same happens over here. I don't want to count the number of states here and the number of states there, because the number of states are enormous. I have to do something else. So what do I actually do? Say, well, because all of this is described by microcanonical ensemble, right? So I can use this description of the entropy. Right? This still works. Why it works? Because I started with microcanonical ensemble, and that's fine. All right. So instead of writing S as a function of omega, I'm saying that S divided by K Boltzmann to the power of E, right, equals to omega. So instead of writing the probability in terms of the number of states, I want to write the probability in the terms of entropies. Yes? Question? No? Okay. So what we obtain is that Fi equals to e to the power of S. Now it's not S, it's global S. It's S of the reservoir. Okay? Where the energy, you have to define an energy for a specific entropy. E total minus EI. And we have 1 over K Boltzmann over here. In the denominator of this fraction, what we have, it is E to the power 1 over K Boltzmann. Now it S of the total system of E total.
How come the omega of EI in the system doesn't matter?
Because it's not. How do you compute probability? So for the dices that I have, for example, what was the probability of getting 1? You have to count all the possible states in the whole system, which are concerned only the the black dice and the red dice. So think about the example. The example of 3 dices. In order to compute the probability of the green dice to get a specific number, you have to count the number of states of the black and red dice.
But in our system, don't we want to increase the omega?
We can do a lot of things, but for this probabilistic, is this okay? That's the question. And the answer is, if you want to calculate probability, you need to calculate the number of states that corresponds to this specific EI, all right? And divide it by the total number of states. That's it. And this comes from the conditional probability formula. Okay? Yes?
The reservoir is also microcanonical ensemble?
Yes. Everything here, in total, this is, so the total system is described by microcanonical ensemble. Yes.
But the system itself is not a microcanonical ensemble.
What do you mean? So let's assume that everything, you don't care about this guy and that guy. Mm-hmm. You look on everything and say, I describe the whole thing by using microcanonical ensemble. Okay? I take a system, I close it, and assume that everything is homogeneous. Now I'm taking a part of this guy, and I'm focusing only on it. That's it. And out of this, a magic happens. Right? Okay, next step. So what do we do? What do we do in our next step? First of all, let's look on S total. It is E total. What do we know about entropy of any system? What it has to be? It has extensive, right? So we can write it down as a system as of the entropy of our system plus the entropy of the reservoir, right? Because we have two parts, the heat bath and the system. The entropy of everything is the entropy of the system and the entropy of the heat bath. Okay. But, and here is the trick, where I want to compute it. I pick up an energy and I say, let's assume that I have an average energy E, and I want to compute the entropy of the system, provided my system sits in a state where the energy is average. Okay? So if the energy of the system is E, the energy of the reservoir is E total minus E. Okay? So this is extensivity. So we're starting to separate this guy. Let's do something about the reservoir itself. Again, why I'm doing all those tricks, the formula that I just read is enough. You go and count states, but nobody really wants to count anything. It's hard, okay? And physicists not as lazy as mathematicians, but they're still lazy. Okay. So what do? We do on S reservoir of E total minus EI. And I'm just saying that it is E total minus E minus E minus EI.
Minus EI minus E.
Minus EI minus E. What do I have here? Just a second. It's plus. It's plus. E minus EI. Okay. So I subtracted and added E inside the system. Okay. And now I'm doing a Taylor expansion. So what happens in my Taylor expansion? S reservoir of E total minus E. Why I have done it? Because you see, here I already have S reservoir of E total minus E. So I'm getting something in the denominator and in the numerator, which should cancel out. Okay. And plus ds reservoir d watt, whatever, dE, right? And here I have E minus EI. Okay, and here I have 1/2 d squared s dE squared something plus 1 3 factorial d3s dE to the third power, etc., etc., etc. So first of all, let's look on this guy. What is this? What is ds to dE?
The temperature of the reservoir.
But it's the temperature, or it's
1 over.
1 over temperature.
Beta.
So it is 1 over the temperature. Okay? And here comes an assumption. Strong physical assumption. You can play with math. You say, oh, it's a conditional probability, I count states, etc., etc., etc. Physics has to enter somewhere hard. And this is the first strong physical assumption. Okay? You say, the reservoir has a constant temperature T. So whatever we do, so there is an exchange of the energies between the system and the reservoir. The temperature of the system is constant. Usually you say, well, my heat bath is enormous, it's huge, it's wow, it's the size of the universe, right? T is constant, so any energy that comes inside, it's somehow absorbed, and the temperature of the reservoir is not modified by anything, right? So this is a physical assumption. So the moment that T is constant, what happens to all those additional derivatives?
0.
Cancel out. Why? Because T is constant. Okay? So the first derivative is constant, and you take this next derivative, cancels out. Okay, this is a very strong physical assumption. You can question it. Does it happen actually? Okay? So there are two questions so far. One is that T equals constant, and the other one, is there actually a specific energy E that the system can have? Okay? I assume that this E, which is the average energy of the system, right? The system can actually have it. So this is another assumption that we use. All right, so if T is constant, let's erase this. We don't really need it anymore. We obtain the following. S reservoir of E total minus EI equals to S reservoir of E total minus E plus 1 over T E minus EI. Okay, so that's enough. Let's plug all that we have achieved so far in the formula. So Fi equals to e to the power 1 over k Boltzmann. What we have inside? So we have S reservoir E total. So instead of S reservoir E total, we put S reservoir E total.
Stas, it's S reservoir minus E, not minus AI.
Minus E, yes, thank you. Thanks. Minus E plus 1 over T E minus EI divided by E to the power 1 over k Boltzmann. So what we have as system at E, as system at S system at E plus S reservoir of E total minus E. What cancels out? S reservoir, S reservoir. Okay, and we are left with. So let's put everything in the denominator and don't look on the fraction. So we have S, what we have, 1 over k Boltzmann, S system at E with minus. We have minus 1 over T E, and we have plus, thank you, and we have minus we have K Boltzmann over here. We have K Boltzmann. We have minus 1 over K Boltzmann T EI. Okay, so I want to write it down as E to the power minus 1 over K Boltzmann T EI. And here I have E, or 1 over K Boltzmann T E minus T S of the system. And we have a very, very nice formula. What is this formula? If you want to calculate the probability of the system, it's connected somehow to a heat bath, your reservoir. The temperature of your reservoir is constant. The canonical ensemble tells you that Fi equals to e to the power minus beta Ei, where beta is 1 over K Boltzmann T. Here you have e to the power beta F. What is F? E minus Ts is the Helmholtz free energy. Right. This is a very nice connection to thermodynamics. Why? Well, in order to calculate probabilities, you need only the energy of the specific state, and there you have a connection to your free energy of the system. Now, if you say, well, Stas, it's a damn formula, there is a mixture of microscopical behavior, which is this EI, and macroscopical behavior, thermodynamical function, which sits inside, and it's a bad mixture. What can I do? And the answer is, well, you can use normalization. Remember probability. Probability says that summation of I, Fi, has to be equals to 1. It's the second axiom of Kolmogorov for any probability that you can define, even for this probability. When you sum over all the possible outcomes of your experiment, the total sum has to be equals to 1. Okay? So what we have here the following thing. So what is sum of I, Fi? It equals to a sum over I, e to the power beta f, to the minus beta Ei. Okay, beta f. Okay. Take this guy outside of the sum. You have e to the power beta f, a summation of I e to the power minus beta Ei. And all of this equals 1. So what we obtain over here? We obtain that e to the power beta f equals to 1 over a sum over I e to the power minus beta Ei. So let's give a name to this sum. Sum over I e to the power minus beta Ei. Call it z, which is the partition function. Okay. And now we can write down all what we discovered just using the microscopical properties of your system. Okay. What do you have to do? Say, well, if I have a system and I want to describe it using canonical ensemble, what do? So first of all, after all of those, well, constraint, not constraint, condition, not condition, etc., there is a very nice outcome. Fi, probability to be in state I with energy EI equals to E1 over Z e to the power minus beta EI. Z is your partition function over here. Okay. How you make a connection between the microscopical world, because all what you have over here depends only on the microscopical assumptions, constructions of your system. Z is the sum over I e to the power minus beta I. Okay. So you can compute probabilities, you can compute the partition function. The moment that you computed the partition function using only the microscopical perspective and want to deroute to a macroscopical perspective, mainly thermodynamics, you use this, right? So e to the power beta f equals 1 over z. Let's take a log out of both sides. So log of e to the power beta f equals to log of 1 over z. Right? And we obtain minus log of z equals to beta f, and f, this is the free energy, equals to minus 1 over beta log of z. Okay. So now you have an algorithm, right? And it's different than microcanonical ensemble algorithm, right? What is different? The main difference is, instead of counting the number of states and then count after you counted the number of states, which is hard, to count states is actually really hard, because you do it for a constrained system, for a specific energy. But here, you don't care, the constraints disappear. You somehow smooth those constraints in the possibility for the system to be not in a very specific state, very specific energy. The system can change its states. It can change its energy. The energies of the system is not conserved. Why? Because it can exchange the energy with the heat bath. Okay. So, but what you obtain, you look on the system, you say, I only need the different the energetic spectrum of the system. The moment that I know the energetic spectrum of the system, I can compute probabilities. I can compute probabilities, well, I can compute the partition function. I can compute the partition function, I can compute the free energy function. I have the free energy function, well, whatever you want I can compute out of this free energy function. I can compute pressure, I can compute chemical potential, whatever we have learned in thermodynamics introduction, you can obtain out of this free energy. That's it. You're done. Right? It's of course easier said than done, because you still need those guys, right? But it's much more easier than to count states. For example, if you want to compute the energy, right?
What is the EI?
What are the EIs? Exactly. What are the EIs? It will depend on your model. Provide me a model and I will find EI. Right? If I want to compute E, right? If I want to compute E, so I can go from here, okay? I can go from here, from the Legendre transform, or I can say, well, what is E? E is the average energy, right? So it's the expectation value. If it's the expectation value, so I can use definition that somebody taught me in probability and statistics for physicists. And it is a summation over I, EI, FI, right? This is just a simple definition. The moment that I have it is sum over I, EI, 1 over Z, e to the power minus beta, EI. Okay. How do I compute it? I need a little bit more nicer expression. I can use this form. This is fine. This is more than fine. This is excellent. But if I want a closed formula that maybe somebody wants to memorize, I don't remember the formula, but let's develop it. So what do? We take 1 over z out. And here we have this EI. And here we have EI e to the power minus beta EI. Okay, I need to compute the sum. And this sum, and this is a nice trick, we use the Feynman trick. Feynman trick. You know what's a Feynman trick? It's usually used for integrals. It's a very, very, very powerful technique to solve integrals, but also to solve summations. You take a derivative out of something, you present whatever you're integrating on as a derivative with respect to some parameter. So I'm looking on this is EI. I'm looking on this, I have 1 over z, EI. I'm looking on this, I'm saying, oh, if I'll take the derivative, look just on this guy. If I'll take the derivative of this with respect to beta, and I multiply it by minus, I will have EI over here, right? So this is minus d to d beta of e to the power minus beta EI. Do you agree with me? Okay. So, very nice. And this is the power of Feynman trick. It's, well, yeah, you always can describe it as, well, it's sometimes not useful, but you describe it as some derivative. But the derivative is not with respect to some index or EI. It's with respect to something that you can get out of the integral or get out of the sum over here. Okay, so I have 1 over z minus 1 d to d beta, and all the notations here, don't worry, the sum is converging homogeneously everywhere, so this is fine. I'm not breaking anything. Okay.
The sum is simply the partition function.
Yeah, but why can you do this? This is a heavy mathematical question.
Because it's not dependent on I.
So because the sum is converging b'midah shava. I don't remember what's the English translation. E to the power minus beta I. And the last term, this one, right? It's just what we have over here. You see? So what we obtain equals to minus 1 over z d to d beta of z. If I want to write it as minus d to d beta of log of z. So this is a very nice closed formula. E equals minus d to d beta of log of z. If you really want to memorize it, I never remember it. Because this is enough. You want to compute energy? You have a formula, or you can use the definition of probability. You want to compute the free energy? You have a formula. Everything is nice and compact. So how we solve something using it? What we actually do? Because it's very nice that I can have closed form formulas for the energy, for the probabilities, for the free energy, but the elephant in the room is the following object. What are my EIs? How do I compute them? Okay, so again, the question is, you need to compute the partition. To understand anything, you need to compute the partition function. If you want to solve anything using the canonical ensemble, you need to compute this object, which looks nice, but it's actually very, very, very hard to compute in most cases. And sometimes it's impossible, or in most cases it's actually impossible. So how still we can compute it? How still we can compute this guy? Okay? So there is only one way that physicists know well, there's some actually, but I'm not completely telling you the truth. There are specific situations that specific techniques are known, but 99% of the cases that we are capable of computing the partition function, and out of the partition function you can compute energy, free energy, whatever, is the following. If you have an ideal gas, right? So I told you that physicists know how to solve only two problems: free particles and harmonic potential. Okay? It's everywhere you go, eventually you will either say, oh, I have free particles, or I have a harmonic potential. In analytical mechanics, have you been told, you seen Hamilton-Jacobi theory? Yeah. So Hamilton-Jacobi eventually tells you that by some crazy geometrical deformations, you can bring everything to either free particle or harmonic potential. The same case over here.
What about the two-body problem?
What the two-body problem is eventually two problems, right? And one of them is going to be free particle, and the other one is going to be harmonic potential in some crazy coordinates.
But I feel like the two-body problem is basic for almost all not a harmonic potential problem.
It's just because you don't know how to find the right coordinates. It's your problem, not mine. Okay? Find the right coordinates. That's what Hamilton-Jacobi tells us. Now, the same goes over here. Well, it's not true. We don't know how to solve problems with interactions. We do know how to do it, especially if those interactions are limited. But the technique that we always use is in the spirit of the Hamilton-Jacobi. We say we have a system with a lot of interactions around it, right? And this particle is interacting with that particle, as in real life, because real life is not gas, ideal gas. But we say the following thing. Let's describe all those different particles using a different set of coordinates, using a different description. And in this different description, so those particles will look like as if they are not interacting. So what we are going to do is we are going to, well, I will describe to you how it's solved when the particles are indeed not interacting. But what we're going to do from now on until the end of the class is to look on different systems using canonical ensemble, grand canonical ensemble, doesn't matter. Look on different systems and say, well, there are interactions. But if I'll stand on my head and I'll turn my right leg up and my left hand down, oh, those particles will look to me as if they're not interacting. They're not my original particles, they're something else. Quasi-particles. But those quasi-particles are not interacting between each other, and then I can use the technique for solving the partition function for non-interacting particles and obtain everything. So the goal is always to look on a system which is complicated. It's always complicated. Ideal gas it's nothing. People know how to solve ideal gas for centuries, right? But the problem is always to look on a problem which is hard and somehow transform it to a problem which is easy. And this is what physicists do no matter in what field. They take hard problems, they stand on their head, they raise the one hand up and they say, oh, now it's easy. And this is what we're going to do. I will describe to you the idea for a simple system of two particles that are not interacting. And next week I will describe to you the general mechanism. So,
Wait, Stas,
yes?
you said we do this until the end of the class, you meant until the end of the course? Like this is all we do in statistical?
So all we're going to do from now on, we're going to take hard problems and describe them as non-interacting particles. Okay? That's it. So if you know how to do it on your own, you're free to go. Right? But it's hard. So the number of hard problems that physicists can solve, it's really hard. Because eventually the method, mathematical, analytical method, so you can take a very crazy system and you can push it inside a computer or produce a code and simulate it. It's okay and it's fine. But in order to solve it analytically, there are very limited amount of methods that you can do. So there are beautiful physics that is concerned with high energies, etc., but it's usually non-interacting. The moment that you have interactions, any system becomes almost unsolvable. Very, 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 very fast. unless you find a way to describe it as a bunch of harmonic particles, harmonic oscillators, or something like that. So let's see the idea how to find or to obtain Z. And the idea is, let's look on the simple system, and you can ask me, wait, Stas, you developed it for a macroscopical system, right? So you look at the system, you use the extensivity, you have to use macroscopical systems. And you'll be correct. But let's, for the sake of the argument, look on the very simple system. I have two particles. They're absolutely not interacting. Okay? And each of those particles, so this one is going to be red, and the other one is going to be green. Red, green. Everybody are capable of separating red and green? Okay. So let's assume that we have red and green particle. They are not interacting. The green particle have energy E1, 1 and E1, 2. The red particle, switch the colors. The red particle is going to have energies of E2, 1 and E2, 2. Okay. Those are the different energies of these two particles. They are absolutely not interacting. When I have to compute the partition function, Z, I sum up over all the possible states of my system, okay, e to the power minus beta ei. So what defines a state? The state is defined by the energy that is in this specific state. So for this simple system, what are the different states? So we can say, all right, we'll take E1, 1 and E2, 1. We take E1, 1 and E2, 2. We take E1, 2 and E2, 1 and we take E1, 1, 2 and we take E2, 2. Those are the different configurations of the system. So in total we have 1, 2, 3, 4 states. Each state, let's call it I equals 1, I equals 2, I equals 3, and I equals 4. Okay? The energy E1 equals to E1, 1 plus E1, 2. The other state, state number 2, it is E2, and it is E1, 1 plus E2, 2, etc. E3 equals to E1, 2 plus E2, 1, and E4 equals to E1, 2 plus E2, 1. Now, according to this prescription, we have to do the following. We have, like this marker, we have to sum, right? So what we have, e to the power minus beta e1 plus e to the power minus beta e2 plus e to the power minus beta e3 plus e to the power minus beta e4. Very nice, very simple for this simple system. Okay. But we can perform this summation slightly differently. We can do the following trick. So this is EI, e to the minus beta, EI. Okay. So let's do this and say, well, actually, what is EI? EI is combined as it is a sum of energies of two different particles. So I sum over I, e to the power minus beta, and here I have E1 plus E2. And have a minus sign over here. So look, we summed up over all the different realizations of E1, E2, E3, E4, but it's actually summing up over all the different realizations of E1 and E2. Now, saying, okay, but you know what? I want to sum it a little bit differently. I don't want to go and write down all the possible realizations and then plug them inside. I first want to sum up over what? Over the realization of E1. So this sum is sum e to the power minus beta E1 multiplied by e to the power minus beta E2. And I sum up over all the possible realizations of E1 and E2 in the different states 1, 2, 3, 4, 5. Now this sum, I can say, let's first sum over all the possible realizations of E1. So it equals to e to the power minus beta E1, 1 multiplied by all the possible realizations I over e to the power minus beta E2I plus e to the power minus beta E2, 1 multiplied by all the possible realizations of e to the power minus beta E2I. Right? I can do this. I can resum. Instead of summing over everything together, I'm saying I'm summing up first over all the possible values of E1, and well, I will sum up over all the different values of E2 later.
So basically, you're going to write a partition function for each particle.
Ah, yes, yes. But wait. So, okay, this term is not that term, but this is exactly like this. Okay. So what I obtain e to the power minus beta E1, 1 plus e to the power minus beta E2, 1 multiplied by the sum over I e to the power minus beta E2I. Right? I just have taken this part, which is exactly the same, but multiplied this term and that term. And look what I've got. Instead of writing this as E plus E, I'm writing it as, well, Z equals to sum over I, e to the power minus beta, E1I, multiplied sum over I. It doesn't matter what's the index, so let's make it J, e to the power minus beta, EJ2. This is what I managed to achieve. Now, well, yes, mathematically correct, mathematically true, but if you look on two systems, so now we had a system that was combined of two particles. But let's assume that we have, instead of one big system, two systems. This is system 1, and this is system 2. The partition of system 1 was Z1 equals to a sum over I e to the power, no, this is Z2. Z2 sum over I e to the power minus beta eps E2I. This is Z2. If we had just one single particle with two energies, this is going to be Z2. The same applies to a system constructed of one single particle with two energies. So Z1 equals to a sum over I, e to the power minus beta, E1, I. So we have Z2 and Z1. So what we managed to obtain that Z, the partition function of the total system combined from two particles, it is Z1 multiplied by Z2. Okay? And this nice trick is called factorization.
This trick only works if the systems are not coupled.
Exactly. So I will generalize this trick. For any system combined of particles that are not interacting with each other. Any system that looks like an ideal gas, okay? Gas of harmonic oscillators, gas of whatever, okay? If I have a system that's combined of something which are of many different particles that are not interacting between each other, this factorization trick can be performed. And what it means that instead of computing a partition function of a huge system with a huge number of states, here it's 4, I can go and compute partition functions of single particles. Okay? How exactly, what I do, but this is the only trick that we know. We know how to compute partition functions of large systems just by performing these factorizations. If we don't know how to factorize, we are lost. How exactly we factorize, what we do in the general case, we'll all see it next week. Thank you. כן. לא, אני חושב שאתה מתחיל מהרובוט, תלוי מאיפה אתה מתחיל. אתה מתקרב לקרבוס קלפרון, נכון? אז אתה הולך, תלוי מאיזה פאזה אתה מתחיל.